Section 9.5, alternating series, absolute convergence, and conditional convergence. First, we need to define an alternating series. An alternating series is a series of the form -1 to the n plus 1 times a to the k, or a1 minus a2 plus a3 minus a4 plus a5, etc., where all of the an are greater than 0 for all n. Theorem A, the alternating series test. Let a1 minus a2 plus a3 minus a4, etc. be an alternating series with the nth term, an, greater than an plus 1, greater than 0. So we're looking at the absolute value of those terms, and they are decreasing. And if the limit as n goes to infinity of the nth term is 0, then the series converges. Moreover, the error made by the sum of the first n terms to approximate the sum of the series is not more than the n plus first term. So let's take a look at an example. Show the alternating harmonic series converges. And then how many terms of this series would we need in order to get a partial sum Sn within 0.01 of the sum of the whole series? To show the alternating series converges, there are two parts to the test. You need to show that the nth term is greater than the n plus first term for all n, and here the nth term is at 1 over n. The n plus first term is 1 over n plus 1, and if we add 1 to the denominator, we're making the fraction smaller. So in fact, the nth term is greater than the n plus first term. Then we need to look at the limit as n goes to infinity of the nth term, and we need that to be 0. So that's the limit as n goes to infinity of 1 over n. Again, we're looking at, for this part of the test, the absolute value of the term. And that limit, in fact, does go to 0, so this alternating series converges. If either parts of this test failed, we would say the series diverges. Second part, we want the error term to be less than 1/100th when using the nth partial sum to approximate the sum of the series. We know that the error term is less than 1 over n plus 1, and we want that to be less than or equal to 0.01. So solving for n, we're going to multiply by n plus 1 on both sides and divide by 0.01. So swapping sides, I get n plus 1 is greater than or equal to 1 over 100th, which is 100. So subtracting 1, n has to be greater than or equal to 99. So we would need the 99th partial sum to be within 1/100th of the actual answer. Example 2. Show the series 1 over 1 factorial plus 1 over 2 factorial minus 1 over 3 factorial, etc. converges. So first, we recognize this to be an alternating series. We're going to use then the alternating series test. And again, we need two parts. We need the nth term to be greater than the n plus first term when looking at the terms in absolute value. So 1 over n factorial is the nth term, 1 over n plus 1 factorial is the n plus first term, and to get from the nth to the n plus first term, we multiply the denominator by something bigger than 1. So the fraction is going to get smaller. So that's going the way we want it to. And then we want to look at the limit as n goes to infinity of the nth term, 1 over n factorial. And in fact, as n goes to infinity, 1 over n factorial is going to 0. So this series converges. Next, we're asked to calculate S5 and estimate the error made by using this as a value for the sum of the whole series. So we want S5, which is going to be 1 minus 1 over 2 factorial plus 1 over 3 factorial minus 1 over 4 factorial plus 1 over 5 factorial. And if you punch that all into your calculator, you get 0.633 repeating. And the fifth error is going to be bounded by 1 over 6 factorial, which is about 0.00139. Theorem B, the absolute convergence test. If the sum of the absolute value of un converges, so if we've got a positive series that converges, then the sum of un converges as well. So if it converges in absolute value, then it'll converge without the absolute value, or if it's an alternating series in particular, it will converge. The series, the sum of un, is said to converge absolutely if it converges in absolute value. So example 3, show the series converges absolutely. To show it converges absolutely, we're going to look at the series without the alternating sign and see if that converges. If that converges, then the series converges absolutely. And this looks just like a problem from previous sections, and we're going to use the ratio test on this. So I want the limit as n goes to infinity of the n plus first term, that's 3 to the n plus 1 power over n plus 1 factorial divided by 3 to the n over n factorial, and that's 3 to the n plus 1 over n plus 1 factorial times, for inverting and multiplying. So now if we simplify, 3 to the n plus 1 and 3 to the n cancel, leaving a 3 in the numerator, and n factorial and n plus 1 factorial cancel, leaving n plus 1 in the denominator. So we just have 3 over n plus 1. And the limit as n goes to infinity of that is 0. So for the ratio test, if the limit is 0, that's less than 1, the series converges. So the series converges absolutely. Example 4, test for convergence or divergence. Here we've got the sum, n going from 1 to infinity, of cosine of n factorial over n squared. So that's a little bit of a difficult series to analyze directly because we've got positive values and negative values, but they're kind of varying in a random order. So let's look at absolute convergence for this series. I know that cosine n factorial over n squared in absolute value is less than 1 over n squared, right? Because the cosine is always less than or equal to 1. And this series converges. So by the straight comparison test, since we've got a series that converges and this series is less than that one, then this series converges as well. And that makes this series converge absolutely. And by theorem B, that's enough to show it, in fact, converges. A series, the sum of un, is said to converge conditionally if it converges but does not converge absolutely. Example 5, show that the series given here is conditionally convergent. So it's an alternating series. We'll do the alternating series test. So if we look at the nth term and the n plus first term, again, we've increased the denominator, so that's going to make the fraction smaller. So the nth term is greater than the n plus first term for all n. And if we look at the limit as n goes to infinity of the nth term, that does in fact go to 0. So this series converges. Now, does it converge absolutely? Well, looking at it in absolute value, the nth term is equal to 1 over the cube root of n. We should recognize that as a p-series with p equal to 1/3, 1/3 being less than or equal to 1, so that series diverges. So it diverges absolutely, but converges as an alternating series. So this is a conditionally convergent series. And that's the end of section 9.5, alternating series, absolute convergence, and conditional convergence. You should be all set now to work on your homework problems. Have a great day.